Good day! With this video lesson, we're going to discuss the topic Understanding the t-distribution under your probability and statistics. Our lesson objectives. At the end of this lesson, you are expected to illustrate t-distribution and identifies percentiles using the t-table. So for our review, a normal distribution can be converted into a standard normal distribution by obtaining your C-value. So let's try to recall what is your C-value. So your C-value or your C-score that will be reflected on your normal curve are only 6. So there are only 6 C-scores allowed in every normal curve. So a C-value is assigned distance between a selected value. So you need to take note of this. So a distance between your selected value, your designated x, so that will be your raw score, and the mean or your population mean mu divided by the standard deviation. Now, the normal distribution property allows to compute a probability problem concerning x or your raw score, because in every raw score there is a corresponding probability. That's why the normal distribution property, so we this normal distribution property allows us, for us to compute the probability problem concerning your raw score or your x into one concerning z. So there is a corresponding value of c in every value of your x, and there is a corresponding value of probability that we can map in each value of your x. Now, to determine the probability that x lies in a given interval, converting the interval to a c-scale. So we need to convert these to a c-scale and then compute the probability by using the standard normal distribution table. Because in your C table, in every C score, there is a corresponding value of area. So this area or areas that we can see in your C table is also a value of your probability. Or we can simply, say that your probability that we can map on your x will be equal to the area or areas, under your C table. So as part of our review or a continuation of our review, now let's deal with this example. So determine the area under the standard normal distribution curve between your C is equal to 0 and your C which is equal to 1.85. So using your C table here, so we're asked to look for the value of area that we can map on your C which is equal to 1.85. So upon looking in your C table, so whatever the point of intersection or area of point of intersection between your 1.8 in your first column and 0.085, in your first row, so whatever the area of intersection between these two will be the value that we can map to the area that we can match, to your 1.85 as your C score. Now, upon looking in your C table, as you can see in this table, so the area of point of intersection, between your 1.8 and 0.05 is equal to 0.4678. So meaning to say this will be the area between your 0 and 1.85. So if you try to look at this normal curve, as you can see, there is a shaded region. So this shaded region from 0 to 1.85 85 here will be equal to 0.4678. So how can we look for the probability notation that we can map on this one? No, because the C value that we can map to this area between your 0 and 1.5, no, if we apply your probability notation, so we can rewrite this one as P of 0 less than C less than 1.85. So the C value that we can map, no, that will represent this shaded region, no, all C scores from this shaded region, no, is in between 0 and positive 1.85. That's why we can say that the probability that we can map, no, for this shaded region is equal to 0.478 because, no, the area is equal to your probability. So once you are dealing with your C score or C value, no, upon looking on your C table, there is a given or there is a corresponding value of your area, no, that we can map in each value of your C score. So this area or areas under your C table will be mapped to the probability, no, or simply this area will be equal to your probability. That's why the probability that we can map from 0 to less than C less than 1.85 is equal to your 0.478. So how can we convert this one to percent? So if we're asked to convert this one to percent, we just simply multiply this 0.4678 by 100. So it's simply 46.78%. So that's how easy we convert this decimal to percent. No, we just simply multiply this area that we get from your C table, then that's it. No, we just simply multiply it by 100. So for your solution now, no, since the standard normal distribution table gives the area between 0 and C value to the right of 0, that is correct, no? We only need to look up the C value in the table. So find 1.8 in the left column. So that's how we look for the value of your area from 0 to 1.85, and whatever the area between your 0.0 area of intersection between your 1.8 and 0.05. So that will be the value that you can map to your C, which is equal to 1.85. Now, the value where the column and the row meet in the table is the answer. So if you're asked to find the area under the standard normal distribution and there is a given value of your C scores, so you need to look for your C table and use it, no? And try to look for the area of intersection of the given value of your C score. Then whatever, no, the area of intersection, that will be the area or the probability that we can map on each C scores, no? So that's how easy we apply, no, or we get the value of your area, no, and if we're asked to find the probability and we apply the concept of your probability notations, so that's how we use it, no? For our lesson proper, William Gaucher was an English statistician who worked for the brewery of Guinness. He developed different methods for the selection of the best yielding varieties of barley, an important ingredient when making beer. Gaucher found big samples tedious, so he was trying to develop a way to extract small samples, but still come up with meaningful predictions. So from this kind of experiment, no, there's a big samples, and William Gaucher get a small samples from these big samples. So meaning to say, if we're dealing with experiment, we're just simply subjecting, no, a sample from a population, not the entire population. So he was a curious, productive researcher that published a number of papers that are still relevant today. However, due to the Guinness Company policy, he was not allowed to sign papers with his own name. Therefore, all of his work was under the pen name student. So he used the pen name student because he was not allowed to sign papers with his own name. Later on, a friend of his and a famous statistician, Ronald Fisher, stepping on the findings of Gaucher, introduced the T statistic, and the name that stuck with the corresponding distribution even today is students T. The students distribution is one of the biggest breakthroughs in statistics, as it allows inference through small samples with an unknown population variance. So this setting can be applied to a big part of the statistical problems we face today and is an important part of this course. So you can use this link or YouTube channel for you to uh, look for this video. So 365 data science. So you can watch this 365 data science as a part of this T distribution. So the T distribution is similar to the normal distribution, just with fatter tails, but assume a normally distributed population. T distributions have higher kurtosis than normal distribution. The probability of getting values very far from the mean is larger with a t-distribution than a normal distribution. So there is a wide range of values for your t-distribution compared to your, if we compare this one to your normal distribution. So here is your t-distribution table. So numbers in each row of the table are values on the t-distribution with your df or your degrees of freedom for selected right tails greater than probabilities. So we only subject your right tail for this t-distribution table. So how can we compute for your degree of freedom? So for example, if there is a given value of your sample n, if your n is 15, then your degree of freedom is equal to 14. So we only subtract 1 to your sample, which is your n. So whatever the resulting value there, so that will be your degree of freedom. Now, in your first column here, this will be your degree of freedom. So your degree of freedom is equal to n minus 1, or simply your sample minus 1 is equal to your degree of freedom. So in your first row here, so this will be the values for your level of significance. So when we say level of significance, uh, this will be the values of the maximum errors that a researcher wants to meet in their researches. So this will be the maximum errors that a researcher wants to meet in their researches. Now, in your confidence interval, in the last row here for your CI or confidence interval, no. So this will be 80%, 90%, 95%, 98%, 99%, and 99.9%. So this will be your confidence interval. So as you can see in this graph for your normal curve here, so we only consider your right tail. So this will be your left tail. This will be your right tail, So in this table, we only consider your right tail, no? So there is a given values here of your degree of freedom. Your first column, in your first row, this will be your alpha or your level of significance. And for the last row here, this will be your confidence interval. So this will be the part of your t distribution table. So how to use the table distribution? So when you look at the T distribution tables, you will see that you need to know the DF, or your degree of freedom. So this means degrees of freedom, and it's just the sample size minus 1. So our step number 1, no, in dealing with your T table distribution, you need to subtract 1 from your sample size, which is your N. This will be your degrees of freedom. So if you're asked to find the value of your degree of freedom or degrees of freedom, then you need to subtract 1 to your sample size if there is a given value for your sample size. Now, for your step number 2 here, no, look up the degree of freedom in the left hand side on the T distribution table. So locate the column under your alpha level. So this will be dependent if your uh, problem deals with your one tail or two tail. So if one tail, we can consider your left tail or right tail. Then if your problem no wants you to deal with a two tail, then need to consider both your left and right tail of your normal curve. So the alpha level is usually given in the question. Always, no? Your alpha level or the level of significance, no, are always given in your problem. So you don't need to look or to compute for this value because alpha level or level of significance are always given in your problem. What you need to do is to know, no, if the problem deals with a one tail or two tail. So if that is a one tail test, no, so we only consider your left or right side of your normal curve. If that is a two tail test, then we need to consider both your left and right sides of your normal curve. For examples, so for a study involving population and a sample size of 21, assuming you have a t distribution, so what row of the table will you use to find the right tail greater than? So probability affiliated with the study results. So our answer, or your degree of freedom, is 20. Why is 20? So how can we compute for this 20? So since your given value for your sample size is 21 here, so we just simply subtract 1 to your sample size, which is equal to 21. That's why the study involving one population and a sample size of 21 has n minus 1, or simply 21 minus 1 is equal to 20. So there's a typo here of n, no? There is no n. Supposed to be there is no n here. So you need to erase this one. So 21 minus 1 is equal to 20. So for number 2, for a study involving a fair design with a total of 54 observations with the results assuming t distribution, what row of the table will you use to find the probability affiliated with the study results? So our answer is 26. So there is a given here 54 as your total value for your population. So a matched pair designed with 54 observation has 27 pairs. So 54 is a matched pair design, no? That's why we need to get the half of this 54 for us to compute for your degree of freedom. So we need to divide this 54 by 2, and that will be equal to 27. Now, 27 now is your sample size. So we need to subject this sample size, or 27 pairs will be your sample size, to be subjected in your uh, experiment. No, the degree of freedom is 1 less than the number of pairs. That's why your n is your 27 minus 1 is equal to 26. So that's how we compute for your degree of freedom. Now we just simply subtract 1 to the given value of your sample size. For number 3, so the t-value of 2.35 from a t-distribution with the degrees of freedom with that is equal to 14 has an upper tail greater than probability between which two values on the t-table. So our answer is 0.025 and 0.01. So for us to visualize more of this, so let's deal with your next slides. So using the table, locate the row with 14 degrees of freedom and look for 2.35. However, this exact value doesn't lie in this row. So look for the values on either side of it. So 2.14479 and 2.62449. So the upper tier probabilities appear in the column headings. No, the column heading for 2.14479 is 0.025, and the column heading for 2.62449 is 0.01. Hence, the upper tail probability must lie between 0.025 and 0.01. So your values should fall in between of these two values from 0.025 to 0.01. Now, if your degree of freedom is 14, then your level of significance is 0.75 and 0.01. And your value should fall in between of these two values. Since there is no exact value for these, then you need to look for the value, no, in between your 0.025 and 0.01. Then you need to consider these two values of your t-value here. So this 2.14479 and 2.62449, this will serve as your critical values. If we're going to plot these two values in your normal curve, this will serve as your critical values that we're going to compare to your computed t-value. Now, if your t-value, no, I mean, your t-value should be less than your critical value or greater than your critical value, no? It should be greater than or less than to your critical value for us to reject, no? For us to reject your null hypothesis. Because if your computed value will fall on the rejected region, then we're going to reject your null hypothesis. Now, this will be, as you can see in your table, no, this part of values in your table, this will be your critical values. Now, if we're going to put this one in a normal curve, these values will serve as the critical values. So as a boundaries between your or as a boundaries between your critical region and the non-critical region. If the computed t will fall in the non-critical region, then you're going to accept your null. Then if your uh, computed t will fall in the critical region, then you're going to reject your null hypothesis. So it is better for us to reject your null because as a researcher, no, we always want to see differences between your variables involved. So if we assume no, because since null shows us equality between your two variables involved, for example, if we consider x sub 1 as your first variable and then your x sub 2 as your second variable, so if we're going to deal with your null, x sub 1 will be equal to your x sub 2. So as a researcher, we always want to prove and we also want to look for the differences between these uh, uh, two variables. So it's a nonsense to deal with a variable with the same characteristics, same values, and so on. So definition of terms, a t-distribution is a distribution of values less than 30. So we use t-test. Now, for example, we use t-test for to see differences. We always look for, if we're asked to look for the differences, for example, if there is a significant difference now between your post-test and pre-test, so we simply use t-test for us to look or for us to see if there's a significant difference between your pre-test and post-test, the results of these two tests. No? The degrees of freedom denoted by DF are the number of values that are free to vary after a sample statistic has been computed, and they tells us the specific curve to use when a distribution consists of a family of curves. So the concept of the degrees of freedom is used in the T distribution. So there is no probability that we can deal on your T table without dealing with this degree of freedom. Because before dealing with your T table, you need to look for the value of your degrees of freedom, or simply your df is equal to n minus your 1, or 1 minus, or I mean your sample size minus 1 is equal to your degree or degrees of freedom. So for examples, for number 1, if the mean or the average of 5 values is 10, then 4 of the 5 values are free to vary. But once the 4 values are selected, the fifth value must be a specific number to get a sum of 50. So therefore, no, your n is equal to 5 and your degree of freedom is equal to 5 minus 1, so that will be equal to 4. So that's how easy we compute for the value of your degree of freedom. We just simply subtract 1 to your sample size n. Then for number 2, a recent study of 16 students of Marami High School, Camiling, Tarlac, showed that the mean of the distance, no, they traveled to go to school was 10.2 kilometers. The standard deviation of the sample was 2.3 kilometers. So find your t sub alpha over 2 using the 99% confidence interval of the t distribution table. So your sample size is equal to n, which is equal to 16. Then confidence interval, that will be equal to 99%. So find the value of your alpha over 2. So here, we're dealing with a two-tailed test because we divide your alpha by 2. So we need to consider both sides of your normal curve. So since we're dealing with your two-tailed test, then we need to divide your alpha or your level of significance by 2. So using your confidence interval, which is equal to 99%. So since the 99% confidence interval is to be used, your alpha now, so this will be your alpha. Your alpha is equal to 1 minus 0.99. 1 here is the total area in your normal curve, no? So your 0.99 here, no, we just simply convert this 99% to decimal. So we divide 100. So 99 divided by 100, so that will be equal to 0.99. So we're just simply converting this 99% to decimal, that will be equal to 0.99. So 1 minus 0.99 will be equal to your level of significance alpha. Now, your alpha now is equal to 0.01. So that's how we compute for the level of significance. So your level of significance, or alpha, or your alpha level, is equal to 1 minus your CI. Your CI is your confidence interval. Now, after getting the value for your alpha, you just simply know the value of your alpha now from your 1 minus CI. So your alpha now over 2 is equal to 0.01 over your 2. Because we're asked to find the value of your alpha over 2, then that will be equal to 0.01 over 2, or simply equal to 0.05. So the value for your alpha over 2 is equal to 0.005. Now, for step number 2, find the t sub alpha over 2 in the critical values of students' t distribution table below or in your next slide. use 99% confidence interval with DF is equal to 15. So it is 2.947. So for us to visualize this one, so let's try to deal with the next slide for your t distribution table. So here is your t table. So find 15 in the left column and 99% in the top row. So the value where the column and the row meet in the table is the answer. So that will be 2.947. So same thing with your C scores. No, so whatever the value between your no, whatever the value of your area section, area of intersection, that will be the uh, area or probably that we can map in each C score. So same thing, no, on how we look for the T critical values in your t-table. So using your values of your degree of freedom, your degree of freedom is equal to 15. So that will be equal to n minus 1 or 16 minus 1. So that will be 15. Then we're looking for the 99% interval and we're dealing with a two-tailed test. So we're dealing with the two-tailed test. So that will be your alpha over 2 is 0.005. No. Now, your critical value now is 2.947 because this will be the point of intersection between your degree of freedom and your confidence interval here. So for us to visualize more the given values in the given problem, no. So our critical values is negative 2.947 and positive 2.947 because since we're dealing with the two-tailed test, so a while ago I said that we need to consider both sides of your normal curve. That's why we divide also your level of significance alpha by 2 because this alpha over 2 this is equal to 0.005 will represent the area of the shaded region after after your critical values. So the area after your critical values will serve as your critical region now. So the area, no, or the class interval between your positive and negative critical values. So this will be your class interval or the non-critical region. So this will be your NCR or the non-critical region. Now, if your computed value will fall here, no, somewhere here in your critical region, you're going to reject your null hypothesis. Same thing with this one. If your computed t-value will fall here in your critical region, you're going to reject your null hypothesis. If your computed t-value will fall in the non-critical region, meaning to say you need to accept your null hypothesis and you need to accept that your variable 1 will be equal to your variable 2. Your assumption that there is an equality between your two variables should be accepted. Why? Because your computed value fall no under your non-critical region. So that's how we use your normal curve and the critical values no for us to see if we're going to reject or not your null hypothesis. So for example number 3, a random of families in a particular street resulted in the following family sizes. So 6, 7, 5, 4, 2, 8, 3, and 9. So find the t sub alpha over 2 using the 95% confidence interval of the t distribution table. So our solution, so if we're going to consider these families, so there are 8 families here. So your 8, your sample size is equal to 8, then your degree of freedom will be equal to 8 minus 1 or simply 7. Now, your confidence interval is 95%. Again, your alpha, no, or your level of significance or alpha level is equal to 1 minus your confidence interval. So find the alpha over 2. So since 95% confidence interval is to be used, then your alpha or your level of significance is equal to 1 minus 0.95 or simply 0.05. So if we're asked to compute for alpha over 2, since we're dealing with the two-tailed test, no? So we need to consider both your left and right side of your normal curve. So your alpha is equal to 0.05 and over 2. So that will be 0.05 over 2 or simply equal to 0.025. So this value here, 0.025, is the value of the probability or the area after your critical value that we can see in your t-table after we look for 8. No. So find your t sub alpha over 2 in the critical values of students distribution table below or to the next slide. No. So use 95% confidence interval with your df is equal to n minus 1 or 8 minus 1, that will be equal to 7. So it is 2.365. So using your t table, based on this problem, the answer is 2.365. So the critical values or critical value is 2.365. So find 7 in the left column and 95% in the top row. The value where the column and row meet in the table is the answer 2.365. So this will be the area of intersection, no, between your 7 in the left column and 95% in the top row. So using your t table here, so your df is 7 since 8 minus 1 is 7 and your confidence interval is 95%. So we're dealing with the confidence or CI, the confidence interval is your 95%. So whatever the area of intersection between your degree of freedom and your CI, this will be your critical value. So upon looking at your table, so we get your 2.365 as your critical value that we can map for your degree of freedom, which is equal to 7, and your CI or your confidence interval, which is 95%. So we're dealing with the two-tailed test. So your alpha of significance is 0.025, no? Your alpha is 0.05. Dealing with your two-tailed test, then this will be your critical value now for that we can use in your normal curve for us to check if we're going to reject or not your null hypothesis. So the importance, so the t distribution and then the associated t scores are used in hypothesis testing when you want to figure out if you accept or reject the null hypothesis. Using the values of your confidence interval and your your DF or your degree of freedom, no, using your T-ball, you can look for the value of your critical values there. Now, after getting your critical values, you're going to plot these critical values, no? So the area after your critical values will serve as your rejection region or your critical region. So once your computed value for T will fall in your rejection region, meaning to say you're going to reject your null. So if your computed T will fall here in your rejection region, you're going to reject your HO or your null hypothesis. Same thing with the left side. No, if your computed T will fall in your rejection region, you're going to reject also your null hypothesis. If your computed T will fall here, you're going to accept, no, you're going to accept your null. If your null shows that your x sub 1 is equal to x sub 2, for example, then if your computed t will fall here, so you're going to reject this one. Then if your computed t will fall in your acceptance region or the non-critical region, you're going to accept your null. You're going to adopt this one that x sub 1 is equal to x sub 2. So that's how we deal with your T critical values, your DF, and your normal curve, especially your rejection region and your acceptance region. Rejection region is your critical region, your acceptance region that will be your non-critical region for another term. So thanks for watching. If you want to like, comment, share, and subscribe, so please do so. I'm Arvin Enriquez, your subject teacher for probability and statistics.